All right, today we are focusing on 5.7, solving quadratic inequalities. We are going to look at some examples, and you remember your quadratic inequalities keep all the properties of your linear inequalities, so dashed and solid lines as well as shading. So when we look at this, we want to fill in our notes. We have a quadratic inequality, in two variables. Can be written in one of the following forms, where a, b, and c are real numbers, a is not able to be 0, and its solution set is a set of ordered pairs x and y. So we're going back to the y equals ax squared plus bx plus c. The difference is, instead of having an equal sign here, we're going to have an inequality, and all the inequality rules apply. So if we look, we want to graph a quadratic inequality. First, you're going to graph the parabola that defines the boundary. That parabola will be a solid line if y is less than or equal to or greater than equal to, and it's going to be a dashed line if it is just less than or greater than. All right, then we need to determine where we're going to shade, and we're either going to shade above the parabola if it's greater than or equal to, or we're going to shade below the parabola if it's less than or equal to. And so if I'm looking at this and my y is less than, I'm going to shade underneath this parabola. If y is greater than or equal to, I'm going to shade above it, which happens to be inside. Now, we want to talk about above and below, because if my graph has an upside down parabola, when y is greater, I'm going to shade on the outside above it. When y is less than, I'm going to shade below it. All right, so let's go ahead and get an example. When we look at this, we can see instead of having an equal sign, we have an inequality. The first thing I notice that it's a dashed line because it's less than. All right, graph the parabola that defines the boundary. In order to graph something in standard form, I'm going to use my axis of symmetry formula, which is x equals negative b over 2a. So let's go ahead and plug that in. That's a negative 4 all over 2 times negative 2. This ends up giving us 4 over negative 4. So x equals negative 1. That is my axis of symmetry. And so we want to have that as an anchor for our reflection. So we'll go ahead and draw a dashed line at x equals negative 1. All right, now that we know our axis symmetry, we can find our vertex. And the vertex is found by simply plugging the axis symmetry in for x, and that will give us our y value. So y will equal negative 2 times negative 1 squared minus 4 times negative 1 plus 6. Do some algebra here following your order of operations. Plus 4 and then plus 6. And we get that y equals 8. All right, so that is our vertex. So we're going to go ahead and graph that at negative 1, positive 8. Notice that we have a negative out front. So since our a value is negative, our graph is going to go downward, leaving us a maximum up here at y equals 8. And we also know that it has a 2. So that is going to make it a vertical stretch going down. It's going to be a little bit more narrow than the parent function. Now we can either make a t-chart at this point or get at least an extra point. So I'm going to go ahead with an extra point, and I'm going to use my y-intercept as an easy find. So on the y-intercept, we know that the x value is 0, and that's why I chose it. I'm going to take that 0 and plug it in, and we will get out the value for c. But just to show you that, I get y is equal to negative 2 times 0 squared minus 4 times 0 plus 6. So that zeroes out, y is 6. So using that, I'm going to graph it at 0, 6. And I'm going to use my axis symmetry to help me reflect. So if I'm 1 unit to the right, I am now going to go ahead and graph it 1 unit to the left of my axis of symmetry. And we're just going to get a quick sketch here. Now don't forget, you need a dashed line. So go ahead and draw that going down. You want to fill up your graph because we're going to shade it. So get a dashed line going. And then we have to determine where we're shading it. Now, if I needed a more accurate graph, I would get more points by picking some extra x values. If I needed to know where it intersect on the x-axis for the x-intercepts, I would want some more ordered pairs. If we go back up here, it said y is less than. So if I look at where my graph hits the y-axis and I go where y is less than, I'm going down. So my shading would be inside of my parabola. So we are shading less than. Now, sometimes it's hard to determine or you're unsure of it. So the other way to determine that we are shading below, because y was less than the parabola, would be to use a test point. And the easiest test point to use is 0, 0. So I'm going to take this point 0, 0 and plug it in and see if it's true. 0 is less than -2 times 0 squared minus 4 times 0 plus 6. We've already looked at this when it cancels out. I do get 0 is less than 6, which is a true statement. So if my test point works, then that's the area I shade. If my test point did not work, then I would shade the outside of the graph above it. All right, so we're going to do a couple more examples to practice. And so you can see I don't have any instructions here. It only gives me the example, so I need to remember the process to graph a quadratic and then do some add-ons. So when I go to graph this, first of all, I see that it's going to be a solid line. I also see that it's going to be an upward U and a little bit more narrow than the parent function. Looking at this, I want to find my axis of symmetry, x equals -b over 2a. So I'm going to plug in my x. So it's -5 over 2 times 2. So we are going to get a fraction of 5/4. And since I'm graphing that, I'm going to go ahead and transfer that to a decimal of 1.25. All right, so my axis symmetry is x equals 1.25. So this is definitely a graph that we're estimating. So go ahead to 1 and a little bit more, 0.25. Draw in your axis of symmetry. And now that we have our axis of symmetry, we want to find our vertex. And we're going to find that by plugging the 1.25 in to our formula. So it'd be 2 times 1.25 squared minus 5 times 1.25 minus 2. So this is our y value, which comes out to -5.125. All right. So we're estimating this on our graph. So 1.25, and then we're going to go down to -5 and a little bit more. So there's my point. I need an extra point. So I'm going to use my y-intercept. And I'm going to plug that 0 in. And when I put 0 in, it's going to zero these out and leave me c, which is -2. Now when I go to graph this at 0, -2, I see that I'm getting that upward trend. I want to go reflect this. But since this is at 1.25, I need to go 1.25 units to the right. So I'm at 1.25. So here's a 0.75 plus another half, and that puts me 1.25 units to the right. If that is not easy for you to do, make yourself a T-chart. Put your vertex in the middle, and then build some points around that. So you could go to 0, you could go to 2, build some points in around that, and you'll get a better idea of what your graph looks like. We want a solid line here, so go ahead and fill up your graph. Remember, we're estimating. If we need it more accurate, we'll get more points. And then we need to determine where to shade. And in this graph, it says y is greater than or equal to. So again, if we take a minute and we look at our y-axis, y is getting greater as I go up, which happens to be above and inside the parabola. So y is greater than my parabola. If you want to be sure of your shading and you want to use a test point, the easiest test point again to test the shading is 0, 0. And I put 0 in for y. I will get a 0, 0. I will get out that -2. So is 0 greater than or equal to -2? And it is, so that point should shade, and that is inside the graph. All right, so we have another one over here. and I see that it is y is greater than, so we're going to have a dashed line. It's nice to remember that at the beginning. And our graph is going to go downward and be a little bit more narrow than the graph we just did, as we have an absolute value of -3 is greater than the absolute value of 2. So go ahead and find your axis symmetry. It's x equals a -6 over 2 times a, which is -3. So we get 6 over -6, so x is -1. There is my axis symmetry. Go ahead and jot that down. And now that I have that, I'm going to go back and find my vertex. And that vertex is -1, and we've got to find that y value. So y is -3 times -1 squared minus 6 times -1 minus 7. So go ahead and do the algebra for this. So I end up with 3 minus 7, so I get y is -4. Okay, so plot that. We go to -1, -4. There's your point. And now I need an extra point, so I'm going to go ahead and do my y-intercept. So I put the 0 in, I get 0, 0, and I get out a -7. And so here I go, 0, -7. So I can see that downward movement, 1 to the right. So let's reflect that on our axis symmetry. And I can do a dashed line. Don't forget it's dashed. And then we need to take a minute and determine where to shade. All right, so if we look, it says y is greater. And so if I'm here, I go up the y-axis, it's greater here. So I'm going to be shading above my parabola, which happens to be on the outside. So everything else is shaded in. So we are finding infinite solutions for our graphs. Anything outside of this parabola and above that parabola counts as a solution. Anything on the parabola, because it's dashed, would not work in our inequality. Anything inside the parabola would also be an untrue statement. Okay, now, for these problems that we did, we were graphing the inequalities, and the solutions we have are estimates. We'd have to figure out if they work, if they're close to the line. We are going to now solve quadratics with a more exact form. So this is the part where we're solving quadratic inequalities by using algebra. So we're going to use algebra skills to help us solve and get an exact answer. All right, so quadratic inequalities in one variable, same thing, ax squared plus bx plus c is greater than 0. A cannot be 0 because if it is, it's no longer a quadratic. They have solutions in one variable that have been graphed on a number line. So we're going back to the number lines like this, the 0, the 1, 2. That's what we're going to use to help us. The number lines showing the solution set are going to be divided into 3 distinct regions, and they're called critical values. That is how we break up our number line, with critical values, and I like to abbreviate them as CV. So critical values. The critical values are simple to find. It is factoring that's going to help us find those. All right, so let's look at a problem. Again, these look the same. Instead of having a y equals, though, they have it either equal to 0 or equal to a number. We have our inequality symbol. So first it tells us to write the related equation. Well, the first thing I want to do is I want to set this equal to 0. And so I have an inequality of x squared minus 4x minus 5 is greater than 0. Okay, the related equation is changing out your inequality with an equal sign. So x squared minus 4x minus 5 is equal to 0. So we're going to come back to that. But to find our critical values, we want to write the related equation. Now it says solve the related equation for x to find the critical values. For the problems we're interested in doing, we are going to solve using zero product property. Solve by zero product property. Now, as a reminder, in order to use the zero product property, we are factoring. We have some fairly simple factoring problems to do. So when we go ahead and do this, we're going to take this problem and we're going to factor it, reverse FOIL. So x minus 5, x plus 1 is equal to 0. So remember, we're finding factors of negative 5 that add up to negative 4. And so here are our factors. And zero product property tells us that either this term equals 0 or this term equals 0. So x could equal 5, and we also have x could be negative 1. Now, these are the answers to the quadratic equation. They are not the answers to the quadratic inequality. All right, so how do we find these answers? I'm going to slide my paper up here. We have our quadratic inequality rewritten here, and we want to find the x value in each interval. So the intervals are split by this 5 and negative 1. Remember, these are my critical values. So I'm going to come down to my number line, and my critical values are x equals 5 and x equals negative 1. And I'm going to put open circles, because the inequality was not equal to, at 5 and at negative 1. Okay, now that I have these in here, I have the three distinct regions. I have a region below, in between, and a region above. And so I need to test each region to see which one my solution can fall in. So here we go. I need to test this region. So anything below negative 1 works. So I would like to use x equals negative 2. So I'm going to put a little star there. I'm testing negative 2. In order to test this region, I'm going to use 0. I can use anything in between, and I like to pick 0. So I'm going to test x equals 0. And then to test the above region, I'm going to go with 6. So you can pick any number you want. I just choose to pick the number closest to it, or easiest for me to use, like 0. Okay, so once I plug these numbers in, it's going to tell me whether it works. So up here it says test an x value in each interval. So we have some extra room up here, but I'm going to write down here, we're going to test each interval. And to test the interval, I'm going to take that negative 2, I'm going to plug it into my original function, and I'm going to see if it works. So x squared minus 4x plus 1 is greater than 6. I'm going to come in everywhere I see an x squared, I'm going to put a negative 2. And we want to see if this is a true statement or not. So that's going to be 4 plus 8 plus 1. And I get 13 is greater than 6. And so we have a true statement. And since this is true, then that means anything below this line works. So I'm going to go ahead and shade in my number line and show that it continues forever. Okay, next thing I want to do is I want to test a point in between. So I pick 0. I'm going to go ahead and plug it into my function. And so that would be 0 squared minus 4 times 0 plus 1 is greater than 6. So I get a 0 is 1 greater than 6. That is not true. And since that is not true, I do not shade this region. Last interval that we need to check, we assume it works, but we want to check it. We picked the number 6. Again, you can pick any number you would like. Plug it into the original quadratic. So 6 squared minus 4 times 6 plus 1, and let's see if it makes a true statement. So we have 36 minus 24 plus 1, and I get 13 again is greater than 6. And so this is a true statement, so I'm going to shade here. Now, we don't want to walk away at this point in the problem, because all we've done is found the critical values, and we found our graph. Our final answer should come as an inequality, stating that x is less than, open circle, x is less than negative 1, or, the statement needs to be or, x is greater than 5. Now, you can write it this way. We can put it in set builder notation, x such that this is true. Or the other way to write it is interval notation. It goes from negative infinity to negative 1, not included, so parenthesis. An or symbol would be your union. And then it starts at 5, but does not include it, and it goes to positive infinity. All right, let's finish one more example before we finish up. And so if I look at this one, it is the same idea. First thing I want to do is I want to set it equal to 0 and find my critical values. So I'm going to subtract my 2, and I get x squared minus 6x, and then this was subtracting 2, so plus 8, and it's going to equal 0. We're going to factor that. X minus 4, x minus 2 equals 0. And the critical values are x equals positive 4 and x equals 2. At this point, we have not solved it. We just know our critical values. So I'm going to go ahead and graph these with a closed circle, since it's an equal to sign, at positive 2 and positive 4. And then I need to test a point. So I'm choosing 0 again. So I'm going to choose x equals 0 and test it. I'm going to pick 3, so I don't have a fraction. And I need to pick something above it, so I'm also going to pick 5. And so these are going to be my test points. So we take a minute, we take our 0, we plug it in. 0 squared minus 6 times 0 plus 10. Is it greater than or equal to 2? So that would be 10 is greater than or equal to 2, and that is true. So since that is true, I'm going to shade everything going down. And then I'm going to try x equals 3. I'm going to plug it in and get the math. So it would be 3 squared minus 6 times 3 plus 10. Is that greater than or equal to 2? So I get 9 minus 18 plus 10, greater than or equal to 2. And that would be negative 9 plus 10. So I get 1 is greater than or equal to 2. And that is not true, so I do not shade it in. And then we're going to test our 5. So 5 squared minus 6 times 5 plus 10 greater than or equal to 2. So I get 25 minus 30 plus 10. Does it work? So I end up with negative 5 plus 10. I get 5 is greater than or equal to 2, and that is true. So this is the other part of my graph. And with that in mind, my final answers, x is less than or equal to 2, or x is greater than or equal to 4. If mine shaded in the middle, it would be an and statement. All right, our last example here has a little bit more to it. We have a coefficient of the x squared, so a little bit more work when we factor. So we're going to go ahead and set this equal to 0. You might choose to move everything to the right side to have a positive ax squared, but I'm going to go ahead and leave it there, and I'll factor out a negative 1. So I'm going to write my related equation to help find the critical value. So negative 2x squared plus 3x, and I'm going to subtract that 2, and that's going to give me a plus 5, and I'm going to set it equal to 0 to help find the critical values. To help me factor, I'm going to take out a negative 1, so I'm left with a positive 2x squared, a negative 3x, a negative 5, and still equal to 0. The factoring is going to be negative 1 on the outside, and we're going to have a 2x in here, and we are going to have a 1x, and we're going to pair this with a negative 5 and a positive 1. That gives me a positive 2x and a negative 5x, which adds up to negative 3. Now that I have that, the negative 1's not affecting my answer, but 2x minus 5 could be 0 if x equals a positive 5 halves. Remember, I'm using my zero product property, so I'm looking at this saying this could be 0. So if 2x minus 5 equals 0, and I go to solve that by adding 5 to both sides, dividing the 2, that's where I got my 5 halves from, or 2.5. My other answer is x could be negative 1. Negative 1 plus 1 is 0, and that's how I zero that out. So these are my two answers. Now I'm going to go ahead and take a minute and graph these. So these are my critical values, and so I want to come in at 2.5, and I'm going to have an open circle because our inequality is just less than, and I'm going to have another one at negative 1. Now once I do that, I need to test my values, so I'm going to go ahead and use negative 2 as one of my test values. I'm going to go ahead and use 0 as one of my test values, and the other test value I'm choosing is right there, and that's at 3. And so I'm going to go ahead and plug these in to my original quadratic, And so I'm going to have a negative 2 times negative 2 squared plus 3 times negative 2 plus 7 is less than 2. This is going to be negative 2 times 4, and I have a plus 3 times negative 2 plus 7 is less than 2. When I put all this together, I get negative 8 minus 6 plus 7 is less than 2. And my final outcome is negative 7 is less than 2. Okay, that is a true statement. So I have another one where I'm shading going down. And so here that is shading going down. I'm going to test my 0, and when I plug that in, it's going to 0 out and leave me just C. So that's 0 and that's 0, so I have 7 is less than 2, and that is not true, so I'm not going to shade in here. We'll find no solutions. Up here we're going to test our 3. So plug it in, negative 2, then 3 squared plus 3 times 3 plus 7. We want to see if that's less than 2. Here's negative 4 times 9 plus, I'm going to go ahead and make that 9 there, plus 7 is less than 2. So I have negative 36 plus 9 plus 7 is less than 2. And I have an error here. So this should be a negative 2. I apologize. Negative 2 there. And that makes this a negative 18. Okay, now that I have that corrected, when I add this up, I get negative 2 is less than 2. And that is a true statement. So I'm going to go ahead and shade that. So my final answers here as inequalities would be that x is less than negative 1, or, that's the key word, x is greater than 5/2 or 2.5. So that would be just written as an inequality. Again, if I want to change that to set builder, I put my x such that, and I put my brackets on the outside. The other way to write this is called interval notation. In interval notation, you can see the lowest point we have is negative infinity. It goes up to and stops at negative 1 but is not included. Union symbol for the word or. It starts just above 2.5 and it goes up to positive infinity. All right, now I want to just take you on a little journey to quickly connect what we just did here with what we did earlier when we graphed these. And so you can see that these look like very different ideas. When we use the algebra to help solve us in the critical values, we actually get down to the exact answers. When we went ahead and graphed it and we made just a sketch of the graph, we don't have the exact answers. We would have to estimate. If I would find the x-intercepts clearly, I would have those answers. This would be a picture of an and statement because it's shaded here. So if you can picture this as a number line, just like we did, and we ignore everything else in the graph, we just have a number line, and we got our critical values, which would be the x-intercepts, we would see that this one would shade going up, and this one would shade coming down, and this would be the overlap, and this would be an and statement. If we look at the graph that we did on the other side, this is also an example of an and statement. So we would have an open circle here and an open circle here, and then this would not have worked. This would not have worked as a critical value, and we would have tested in the middle. We would have found that worked. So if I can take you to this last one here, this one we would find that on our chart, all real solutions would work for the x value, because this would have imaginary solutions since we have no x-intercepts. So last idea to make a connection for you, I have an extra copy of this, and if I would take this graph that we did right here and I transfer it and we make it look like an XY grid. This is just going to be a rough sketch here. This is my y-axis, here's my x-axis. What we found were the critical values at -1 and at 2.5. So I'm not going to take the time and break this down and find the graph, but we know it would be a downward U. I'm not sure where the vertex would be, but if I went ahead and just sketched a parabola in here, and we just sketched it, the idea is when I set this equal to 0, and we had negative 2x squared plus 3x plus 5 was less than 0, or in our case we could put in a y here. If you read it, y is greater than my inequality. And if y is greater than my inequality, I would be shading everything above this parabola. I would shade everything above it and going out here. And the reason I want to show you this is if you can take a minute and think about it, we would have this shaded right here, just like we did when we found our critical values. So if you could compare these graphs, if I actually took the time and I graphed the parabola, I would see this U-shaped curve and I would have everything shaded on the outside, which would shade the values going out, much like we did here when we just looked at it on a number line. So I wanted to show you that there is a connection if you can visualize the quadratic being here, and then that's the shading on the outside. Okay, so that was a look at solving quadratic inequalities.